Assalamualaikum and good day to all. For this week, week 4, we continue about the engineering materials and their properties. So previously we done the lecture about the mechanical properties mostly. For today's lecture, we continue with the other properties such as thermal properties, and then you have electrical properties, and then you have the optical properties and the eco material properties. First, I'm going to explain about the thermal properties. There are two temperatures that are quite common to you, which is the melting temperature, TM, and glass temperature. So the melting temperature is related to crystalline solid, where you have a sharp melting point. And then you have glass temperature, TG, which is related to the non-crystalline. So this solid change into a very viscous liquid. So in engineering design, it's better to define two temperature in a certain range, for example, maximum and minimum surface temperature in either Kelvin or Celsius. So the maximum temperature is related to, for example, melting temperature or oxidation temperature, or you have a chemical change reaction temperature and so on. And also the minimum one, for example, if you using plastic in the sub-zero condition, probably the plastic is unsafe to use because it become brittle, such as example. Another thermal property that you need to know, which is the thermal conductivity, when you can decide whether the material is conductive or non-conductive insulator or dielectric properties and so on. So the rate which is heat is conducted through a solid at steady state. Okay, you call it thermal conductivity. Okay, represent is as lambda or K. So lambda is in unit watts. W is watts per meter Kelvin. So over here, this figure over here, okay, shows how the thermal conductivity is measured. So actually the heat flux Q. So now I'm going about the thermal properties. Probably you already learned in the chemistry, okay, which is you have heat flux Q, which is in watts per meter square, flowing through the material from a surface at higher temperature T1 to a lower one at T2, separated by a distance x. Okay, so over here T1 is the higher one, this one is the lower one, and then you apply the heat over here, and then you apply heat sink over here. So heat sink is to disperse the heat. Over here you put the heating element. Now outside over here you have the insulator, so you put the sample right in the middle over there. Then you can measure the heat flux Q, okay, which is equivalent to minus lambda times delta T divided by delta X, so that you can have a slope which is equivalent to lambda, which is also considered as the thermal conductivity. Here you have the material property charts, which is related to thermal conductivity. I'm sure if you have chance to use the CES EduPad, you can get this kind of chart over here. But from this chart, we can see that this one is related to the HB books. So over here, you can relate to the metals, ceramic and glass, and polymer and elastomer in relation with the thermal conductivity. So you see here you have copper alloys, which is having the most highest thermal conductivity, and then go through the titanium alloy, which is have the least in the group of metals, in the family of metals. Okay, and then over here you have also ceramic and glasses. So ceramic also have a good conductivity such as silicon carbide, over here aluminum nitride, okay, boron carbide, and so on. So at the lower part over here you have concrete, glass, and brick, which is having the least crystallinity, non-crystalline effect. So non-crystallinity also having a low thermal conductivity. And then you have the polymer and elastomer. As you know that this one is completely non-crystalline. So obviously you have a very low conductivity. So the highest one, which is the silicon elastomer, and the lowest one will be the butyl rubber. So mostly the polymers and elastomer is considered as the insulator. The next thermal properties that are related to the previous thermal conductivity, which is the thermal diffusivity in A. Units is meter square per S, is defined by A is equivalent to heat conducted divided by heat stored, which is equivalent to thermal conductivity lambda divided by rho times Cp, where rho is the density, Cp is the specific heat at constant pressure. So the unit will be in joule per kilogram Kelvin. The thermal diffusivity can be measured directly by measuring the decay of a temperature pulse when a heat source applied to the material is switched off, or it can be calculated from lambda via equation 3.13. So of course you can over here is actually the thermal decay, the thermal diffusivity, or thermal loss. So this one is called thermal diffusivity, where you measure the heat loss. The heat capacity or specific heat in unit joule per kilogram Kelvin is the energy to heat 1 kilogram of a material by 1 Kelvin. The measurement is usually made at constant pressure, atmospheric pressure, so it is given the symbol Cp. When dealing with gases, it is more usual to measure the heat capacity at constant volume. So you can use the unit CV, and for gases, you use Cp. So this requires values for Cp. It is measured by the technique of calorimetry, which is also the standard way of measuring the glass temperature Tg. So this figure shows the method to measure the thermal conductivity or the thermal diffusivity over here. So over here you put the material right in the middle of here, then you put the temperature sensor, use the thermocouple, cover in the insulated box, and then you put the energy over here, energy which is a heat source, okay, and then you measure the slope. So you measure the increase of the temperature versus the energy input per kilogram. As you already know, when material is heated, the atoms or the molecules inside the material will vibrate, and then some might cause the material to expand. The thermal strain per degree of temperature change is measured by the linear thermal expansion coefficients alpha in unit Kelvin minus 1, or you can go for the microstrain per Celsius. So if the material is thermally isotropic, the volume expansion per degree is 3 alpha. If it is anisotropic, 2 or more coefficients are required, and the volume expansion becomes the sum of the principal thermal strain. So here you have the temperature change delta T versus thermal strain epsilon, which is equivalent to delta L per L, such as you have learned in the strength of material when you have thermal strain or mechanical strain. So here you put the material or the sample right in the middle in between the heater. The red dot is the heater, and then you have the insulator cover all over here, and then you heat the sample, and then you can observe the increase of length of the sample itself. So from the delta L over here, you can calculate back the difference between the temperature increases and then the original length L over here, and then you can get alpha over here for the linear thermal coefficient or linear thermal expansion coefficient. Another thermal property that you can consider is the thermal shock resistance delta Ts in unit Kelvin or Celsius. So this is the maximum temperature difference through which a material can be quenched suddenly without damage. For example, if you rapid quench a metal, for example, from 200 degrees to room temperature 25 degrees. So you don't have any much difference because the metal have a higher, very high, considerably high melting point, and also the properties does not change. For example, the mechanical strength and so on. So of course, when you do the thermal shock with the glass, for example, and then you might break the glass. And then there are also creep resistance, which is important enough in the high temperature design. Creep is the slow, time-dependent deformation that occurs when materials are loaded above about 1/3 of Tm or 2/3 of Tg. Design against creep is a specialized subject. Here we rely instead of avoiding the use of a material above its maximum surface temperature Tmax, or for polymers it is heat deflection temperature. Another property that is quite important for engineering design, which is the electrical properties. So commonly you already know about electrical conductivity and also electrical resistivity. The electrical resistivity rho C in unit ohm meter. So as you see in the figure 3.16 over here, when you apply sample over here, cylindrical sample over here, which have a fixed length over here, and then you connect it to the voltmeter, for example, and then when you increase the length over here for the sample, you can observe the loss or the reduction of the potential V during the measurement. So the range, you can have a quite a range. For example, the smallest one is like 10 power of negative 8 in units of ohm meter, which is equivalent to 1 micro ohm centimeter for good conductors, more than 10 power of 16 ohm meter. So this one, which is considered a good conductors over here for insulator. When you have the insulator is placed in an electric field, it will become polarized and charge appear on its surface that tend to screen the interior from the electric field. The tendency to polarize is measured by the dielectric constant, epsilon r, a dimensionless quantity. Its value for free space and for practical purpose for most gases is 1. Most insulators have values between 2 and 30. So low density foams approach the value 1 because they have a lot of pores, which is mainly consists of air. So what does epsilon r mean? Or what does epsilon r measure? When two conducting plates separated by a dielectric, it makes a capacitor. So imagine over here you have a plate, two plates over here. Right in the middle, either you put air, not put air, it just remain in vacuum or air. or you can put a material right between the plate, and then you charge it with the potential V, so it become a capacitor. So any charges which is accumulate right in the middle or in between those plate, you have charge Q in unit coulomb, which is proportional to the voltage difference between the plates. So V in volts. So Q, which is equivalent to CV, where C is the capacitance in farad, and then the capacitance of parallel plate capacitor of area A. So you have to actually calculate the area for the plates, and then separated by empty space or by air, or you can put the material in between them, which is equivalent to C equivalent to epsilon A divided by T. Epsilon is the permittivity of the dielectric with the same unit as epsilon naught. T is the thickness or the length between those two plates. So whenever you are applying the potential from the plates, okay, between the plates, so charge will accumulate right in the middle of the between those two plates. So if you put the dielectric material, so you can also determine or you can also measure the charge accumulate right in between them. So from that particular measurement over here, you can get this kind of graph where you can get charge Q versus potential difference V. Then from those slope from these two axes components, so that you can get C, which is equivalent to Q divided by V. So dielectric constants a measure of the ability of an insulator to polarize. So epsilon R, which is equivalent to C with dielectric, and then another one capacity, okay, capacitor properties with no dielectric. So basically you can get this equation. So when charged, the energy stored in a capacitor is 1 over 2 QV, which is equivalent to half of CV power of 2. And this can be large, such as supercapacitor with capacitors measured in farad store enough energy to power a hybrid car. The breakdown potential, which is in megavolt per meter, is the electrical potential gradient at which an insulator breaks down and damaging surge of current flow through it. It is measured by increasing at a uniform rate a 60 Hz alternating potential applied across the faces of a plate of the material until breakdowns occurs. So whenever you have insulator, if you charge the insulator high enough, so you can get transfers from one plate to another plate. Okay, so if the charge is doesn't exceed the capacity of the insulator, then the charge will remain in the capacitor within the insulator. So polarization in an electric field involves the motion of charged particles, electrons, ions, or molecules that carry a dipole moment. In an oscillating field, the charged particles are driven between two alternative configurations, such as shown in the figure 3.18. This charge motion corresponds to an electric current that, if there were no losses, would be 90 degrees out of phase with the voltage. In real dielectrics, the motion of the charged particles dissipates energy and the current leads the voltage by something less than 90 degrees. So the loss angle theta is the deviation. The loss tangent is the tangent of this angle. So figure 3.18 which is the dielectric loss important in dielectric heating as explained in the text. The power factor, which is dimensionless, is the sign of the loss angle and measures the fraction of the energy stored in the dielectric at peak voltage that is dissipated in a cycle. When small, it is equal to the loss tangent. The loss factor is the loss tangent times the dielectric constant. In engineering design, you might want to consider optical properties where you are to determine whether the material is opaque, which is the light cannot go through, translucent, some might go through, but some might diffracted or deflected, and then transparent, almost 90% or almost all of the light go through the material. The speed of light when in a material V is always less than the in vacuum C. So the speed of light is 300,000 kilometer per second. When you have the light going through a certain material, for example, gases or solids and so on and liquid, so you can see the reduction of the speed as well as the deflection or diffraction of the light. As consequence, the beam of light striking the surface of such a material at angle alpha, okay, incident angle alpha, the angle of incidence that enters the materials at angle beta, which is the angle of refraction. The refractive index n, which is dimensionless, is n, which is equivalent to c, which is the speed of light, divided by the speed inside the material, which is equivalent to sine alpha divided by sine beta. Alpha, remember that it is the angle of incidence, and then beta, which is the refraction angle. So it is related to the dielectric constant epsilon d by n, which is almost equivalent to square root of epsilon d. So it is also depends on the wavelength. As light goes through the vacuum, it has the highest speed, which is 300,000 kilometers per second. But as is the light going through gases, liquid, and solid, the atom or molecules will slower the speed of light. So the higher the density of the material, the higher its dielectric constant, and then causing the larger refractive index. So whenever n is equivalent to 1, the entire incident intensity of light enters the material. So n is equivalent to 1 is considered as transparent, but whenever n is much bigger than 1, some light might be reflected. If the surface is smooth and polished, for example, if you compare between the surface of an iron polish with grit 1200 compared to grit 150, so you can see the smooth surface reflected the light and then the rough surface scattering the light. The percentage reflected R is related to the refractive index by R, which is equivalent to n minus 1 divided by n plus 1, and then power of 2 of those equation times 100. So as n increase, the value of R tend to 100%. Last but not least, which is the echo properties. So the embodied energy units in megajoule per kilogram is the energy required to extract 1 kilogram of a material from its core and feedstocks. The associated carbon dioxide footprint in unit kilogram per kilogram is the mass of carbon dioxide released into the atmosphere during the production of 1 kilogram of material. If some material attributes are difficult to quantify, particularly those that involve the interaction of the material within the environment in which it must operate, environmental resistance is conventionally characterized on a discrete 5-point scale, which is very good, good, average, poor, and very poor. So very good means that the material is highly resistant to environment, and then very poor is that completely non-resistant or unstable. The categorization is designed to help with initial screening. Supporting information should always be sought if environmental attack is concerned. So I think that's all for this lecture. So for the summary and conclusions, there are six important families of materials for mechanical design, which is metals, ceramics, glasses, polymers, elastomers, and hybrids. Ceramics and glasses as a family are hard, brittle, and corrosion resistant, and also chemical resistant. Metal is ductile, tough, and good for thermal and electrical conductors. And polymer are light, easily shaped, and electrical insulator. Elastomer have the ability to deform elastically to large strains. And then the properties important in thermomechanical design, and also develop a way of displaying these properties so as to maximize the freedom of choice. So thank you very much.